next question, that is question number 12. And the question is said an infinite long thin wire having a uniform charge density per unit length, that is 5 nanocoulomb per meter, is passing through a spherical shell of radius 1 meter as shown in the figure. A 10 nanocoulomb charge is distributed uniformly over the spherical shell. If the configuration of the charge remains static, the magnitude of the potential difference between point P and R in volt is what? Okay, so we have given that 1 by 4 pi epsilon naught equal to 9 into 10 to the power of 9 and ln of 2 equal to 0.7. So we have to ignore the area pierced by the wire. So the question is basically said there is a line wire, line charge, and there is a spherical charge. Okay, so for this line charge, we have a charge per unit length, that is 5 nanocoulomb per meter, and the spherical charge, the spherical shape which have the charge, that is 10 nanocoulomb. So basically there is a point P at the 0.5 distance from this wire, and 2 meter from this wire there is another point R. So basically we have to calculate the potential difference between these 2 points. Clear? So what we are going to see, let's understand this thing. So now we have to calculate by potential difference on these 2 points, and that will be because of this straight wire and this spherical shell, because they both have the charge. Okay, so how we can approach? So we can calculatively say that the potential difference between these 2 points will be because of this wire and as well as with this shell. Okay, so basically we can write the potential difference between these 2 points, that can be by the potential difference on this point by the wire plus potential difference between these 2 points by the shell. Okay. So we can add and calculate the potential difference by this wire and by this shell, and then finally we can add to calculate the net potential difference between these 2 points. Okay. So now we are going to calculate the potential difference by each way. First of all, we are trying to calculate the potential difference by this wire. So now let's move on the next thing. So by this wire, we can calculate the potential difference like delta V. Okay. And that will be like potential difference at point P minus potential difference at point R. Okay. It can be calculated by the integration method, that is electric field into dr vector, and we are taking the dot product of these two things. Okay. So we can continue, we can see the electric field will be in this direction as well as distance vector also in this direction. So angle between these two quantities will be 0 degree. So cos 0 will be equal to 1. So we can clearly write this. That is nothing but that is E into R dr. Okay, like this. Now we have a limits. So basically the points is going through by the distance 0.5 to 0.5 to 2 meter. So just put the value, that is 0.5 to 2 meter, and solve this again. So finally we can write the electric field by this straight wire, and that is nothing but that is 2k lambda divided by R. Okay, lambda is nothing but that is the charge per unit length. Okay, into that is dr. The limit is going to 0.5 to 2 meter. So just integrate this thing. So the constant will be going out, and that is 2k lambda, and 1 by r, integration of 1 by r, that is ln r. And when we are putting the limits, so you can write that ln 2 by 0.5 to 0.5 like this. Okay, now just solve this thing. So the potential difference by this straight wire will be equal to like 2 into k. K means 9 into 10 to the power 9. And lambda we have given, that is the value of lambda is 5 nanocoulomb per meter. So we can write the value of this, that is 5 into 10 to the power of minus 9 into ln 4. Okay, so ln 4 we can write, that is ln 2 to the power 2. We have a formula ln m to the power n, and this n will be come to the multiplication side, and that will be like this will be cut out, and for this 2 into 9 into 5 into this 2 again, and that is ln of 2. And we have given the value of ln of 2, that is 0.7. So just put the values and calculate this thing. That will be equal to 146 of volt. Okay. So now coming to the next point, now we have to calculate the potential difference between this 2 point by this shell. So we are going to calculate this thing. Next, potential difference by the shell. ये that we have calculated for the wire. Okay. That is for the wire. Now we are calculating by the shell. The potential difference between this 2 point by the shell. So basically, when we are talking about the shell, there is a point that is P point inside the shell. So the potential difference can be written that is KQ by R, because we have to take the whole radius. This is the formula. So now we are going to see the next thing. The potential difference at this point P minus potential difference at this point R. So you can write this like by P point, you can write that is K Q. Q means the charge. Okay. So KQ by R, and R is the distance from point 0 to the radius, and that is can be written like capital R, minus next potential by this on this point because of this shell, that is be KQ by small r. Small r means distance from this point to this, and that is 2 meter. Just solve this. So we can take the KQ as a common inside this, that is 1 by r minus 1 by small r. So the value of this, and that is because of the shell. So the answer will be like 9 into 10 to the power of 9. The charge is 10 into 10 to the power of minus 9 coulomb. 10 to the power of minus 9. Okay. And the value of this, that is 1 by 1 minus 1 by 2. So clearly you can see the value will be like 2 minus 1, that is 1, and divided by 2. So this value will be cut out, and that is 90 by 2. And that is nothing but that is 45 of volt. So the complete answer, potential difference by this 2, that will be like potential difference by wire as well as by shell, and that will be 146 plus 45. So the final answer will be what? That is 146 and 45. So 11, 9, 1. So that is 191 of volt. Okay, so that is with the answer. Thank you very much to watch this video.